Okay. So first, I'd like to thank the organizers for inviting me for this wonderful workshop. My name is Eylon Persky. I'm a postdoc at the Capitonics group at Stanford University. Today, I'll talk about a combination of three experiments, three different techniques that we've done on this half-Oyster compound, yttrium, platinum, bismuth, where the conclusion from all of these is that we think we have a superconducting surface state that breaks time reversal symmetry. Okay, so before I begin, I'd like to thank Aaron and our members of the group. So I'll talk about STM experiments that were done by Alan and mutual inductance that I did with Victor Zhang. And then the samples we get from Claudia Felser at the Max Planck Dresden. Okay, so the structure that I will talk about is the half-Oyster structure, and you can think about it as three FCC lattices that are intercalated together but shifted a quarter of the unit cell with respect to each other, so you get this kind of a zinc Planck plus the extra lattice, and on each site we have a different atom. The cool thing is that with the three lattice positions here, you can choose many different elements, and depending on which elements you choose, you can get many different crystal properties out of this. So it can be magnetic, it can be semiconducting, it can be conducting. Some of them are superconducting. As you go to heavier and heavier elements, you eventually find that there is a band inversion that looks a lot like the mercury telluride, cadmium telluride case, so you can also get topological surface states. The materials that I will focus on today are these yttrium, platinum, bismuth, and I will also talk a little bit about data that we have on lutetium, platinum, bismuth. So these are the ones with the largest band inversion. So they have very robust topological states at the surfaces. Now, the idea is that I'm going to talk about surface superconductivity, but it will turn out that these topological surfaces are not how superconductivity is generated, but there are other things going on. Okay, so the structure, yttrium, platinum, bismuth is a p-type semiconductor. It has this band inversion and a topological surface state, but it is also a bulk superconductor with a low critical temperature of about 0.85 Kelvin. You can see here the transition. This is the resistivity, and here is the mutual inductance. And this is a very interesting case because the carrier density here is very low, and it's in fact one of the lowest 3D, one of the most dilute 3D superconductors that we know of. And also this structure breaks inversion symmetry, so the order parameter in the bulk certainly fits this conference because it is probably some mixture of the singlet and triplet. And there's been a lot of work, both from experiment side and theory, trying to characterize this state, but not a lot has been done to look at the surface, and this is what I will show today. So in order to do this, we have to talk about the surfaces. So both yttrium and lutetium, platinum, bismuth have very similar structures. It turns out that the natural cleavage plane is the 1-1-1 plane. It is actually quite difficult to cleave the samples, but they most likely cleave along the 1-1-1. You can cleave them along the 0-0-1 or 1-1-0, but it turns out that this is extremely difficult to do. If you look at the 1-1-1 surface, you see this hexagonal lattice of bismuth atoms. These are DFT calculations, and these are ARPAS measurements from Claudia, or Claudia's samples, that show the topological surface states here. They turn out to be quite far away from the Fermi level. However, near the Fermi level, we have surface bands, as you can see here in the ARPAS and here in the DFT, that originate from bismuth dangling bonds. It turns out also that this is not just a feature that is specific to the 1-1-1 interface or to the yttrium, platinum, bismuth, but it is quite generic in those half-Oyster compounds and on many different surfaces. But particularly interesting is that there is this Van Hoff singularity here at the endpoint, which can lead to a large density of states. which in principle can drive interesting physics at the surface. Okay, so this is RPS on nice surfaces that they've been able to cleave in vacuum. But it turns out that if you look at the real life surface, it is not the case. Those things are air sensitive. So what you see here is X-ray photoelectron spectroscopy of the surface. And you can see that on this blue curve, there are peaks that correspond to oxygen and carbon. It turns out that this persists several nanometers into the surface. But then you can treat the surface by ion milling and get rid of this. So we know that within, after a few nanometers, all of this junk goes away and we get the actual crystal. Here is a TEM study of a bad crystal, and I'm intentionally showing a very bad one, where the surface is not good. And this is hard to see in this black and white picture, but there is some region here near the surface that looks different than further away. Right there. Okay, if you look at Fourier transforms of these two regions, you find that one of them, so where you get closer to the bulk, it is crystalline, you see nice diffraction peaks, but it looks amorphous close to the surface. If you take higher resolution data, you find that, so this is near the surface, and it's region 2, you find that you have these dark and bright patches, and then it turns out that these are inclusions of platinum oxide and lutetium bismuth oxide. So all of this is to say that when you get this sample, unless you can cleave it, and not for every experiment you can, you get these oxides and junk close to your surface, and this turns out to be important when you try to interpret data taken on the surface. Now, as I mentioned, this is a particularly bad crystal because this region is quite large. Usually these things are just a few nanometers from the surface. So, okay. This is what I said. Okay. Okay, so now this is STM data taken on an uncleaved surface of this material at 300 millikelvin. So the bulk transition temperature is 850 millikelvin. Okay, so you immediately see two things. So one is that there is a superconducting gap. There's coherence peaks. The gap size is 400 millieV. This is quite large if you think of a bulk transition of 800 millikelvin. And there is also this residual density of states at zero bias. And we think that this is coming from all of the junk that is on the surface. So in this case, we couldn't cleave the samples in vacuum, so we measure through this amorphous metallic layer. It turns out that once you do this, you can get something that looks like this V-shape, and the residual density of states is all accounted for by this. And in fact, what we can do is apply a voltage pulse or a current pulse with the STM tip, and then all of this junk is removed, and then we can recover a really nice looking gap. So the density of states really goes to zero. We see the clear coherence peaks. And this you can fit to a Dines formula. Yeah, okay. And then what you get is this kind of a rugged surface where we've removed some of the junk. And now the tunneling can occur through a smaller barrier, so we can get really the superconducting, or the real surface of the material that we would want to study. Okay. We can take this data and fit this to a Dines formula. We leave the temperature as a free parameter to account for electron heating. Okay. Okay, we can do this for various temperatures. So you can see that it's not only that the gap is larger than what you'd expect for the bulk superconductivity, but also that this gap persists to temperatures a lot higher than the bulk transition. And if you plot the gap as a function of the temperature, you find, so here, if you don't take this effective temperature into account, this is the blue dots, but if you believe that the effective temperature that you get out of the fit is the actual temperature, it follows this BCS gap equation. If you assume that TC actually corresponds to a BCS gap of 400 millieV, and you get this 2.8 Kelvin TC. So this is 3 times, or more than 3 times higher than what we get on the bulk. Okay. Now, Okay. Okay. Now the question is, we would ideally want to see whether we can find something like this in different probes, and particularly resistivity. If we believe that this is a surface effect, it will be very difficult to measure with resistance because we have this metallic crystal attached to it. So what we did instead was a mutual inductance measurement. So here we use it's a two-coil mutual inductance. We use the drive coil to apply a magnetic field, an AC magnetic field, to the sample. And then we read out the response from the sample from a second readout coil. And what you see here is the signal, the real and imaginary part of the signal as a function of temperature. So we clearly see this large signal in the imaginary part for the superconducting transition at the correct critical temperature. And it looks like everything else is just flat. However, if you look carefully and you just zoom in this data, there is a change that onsets at around 3 Kelvin, where we start to see something that looks like a diamagnetic response. And we believe that this coincides with the temperature in which we see the STM spectra. So we think that this indicates that either a small volume fraction of the sample or the surface becomes superconducting. If you combine this with the STM, we think this points to the surface. Now I mentioned that this is not that we don't only expect this surface states to occur in yttrium platinum bismuth, but also in lutetium platinum bismuth. The structure is very similar, and indeed what we find is very similar. So the black graph is the pristine surface with all the dirt. There's a big gap here, but there is a residual density of states. Once you do this pulse cleaning procedure, you get 0 residual density of states, clear coherence peaks. The gap remains about the same. It turns out to be larger than in yttrium platinum bismuth. You do the temperature dependence, you find that the IDV spectra, they persist up to 4 Kelvin. Now I do want to say that in different spots on the samples and after different pulses you can get lower temperatures, but we did see that you can get transition at 4 Kelvin. When you measure the mutual inductance, again you see this small response emerging at around this 4 Kelvin. So all of these point out to this picture where we have a surface superconductor that is distinct from the bulk, and it onsets at a different temperature, both in yttrium platinum bismuth and lutetium platinum bismuth. Okay. Now you might not be convinced and wonder whether there is something else on those surfaces that can lead to superconductivity. So we have collected this list of, Okay, we have collected this list of compounds that might be formed out of combinations of yttrium and lutetium and platinum and bismuth. And these are usually what you get for the critical temperatures. So a lot of these are really not compatible with what we see, especially since we get different gaps, different critical temperatures for those states on yttrium, platinum bismuth, and lutetium platinum bismuth. I want to point out, I think tomorrow there will be a talk by Brent Ruchner about this bismuth 2 platinum, which is a very interesting material. I would say if this is the compound that we end up having on our surface, it could be interesting, but I don't think it is. Okay. If you're still not convinced by this, I will now show you the next experiment that we did, which I think will rule out all of these options because it will point to a very unconventional superconductivity, which is not compatible with any of these. So the question we wanted to ask is whether we can understand the order parameter of this surface superconductor. And the experiment that we did was a polar Kerr effect. So we measured the rotation of polarization of light that is, we shine on the sample at normal incidence. And if this surface or the sample break time reversal symmetry, we expect to see a rotation of polarization. We have a very sensitive apparatus to do that in our lab. And here is the experiment that we did. So we start with applying a small magnetic field, few tens of Gauss, and cooling the sample down from a high temperature down to our base temperature, which is 300 millikelvin. And the idea is that if there is a magnetic order, this small magnetic field, you cool through a transition, it will align all of the domains in one direction. And then we can turn this field off. If there is a magnetic order, all of those domains will remain aligned. And we can do the measurement as we warm up, and the signal will decay until we reach some transition temperature where it will go away. Okay, here is the data. So these are two measurements done with opposite training fields. As we warm up, there is a signal. It's not very large, it's a fraction of a microradian rotation, but it's there. If we reverse the training field, we align the domains in a different way. The sign of the signal is reversed. Lo and behold, the transition temperature, 3 Kelvin. So this matches what we see with the STM and what we see with the mutual inductance. So this is yttrium platinum dissonance. I would also point out that if you compare this to other chiral superconductor candidates, the size of the signal is on the same order of magnitude. Okay. So the next thing I want to point out is there is this one point here at the very lowest temperature where there seems to be this non-monotonous behavior. And we were very bothered by this. You see it in both cases. So we wanted to investigate this further. Note that this is just below where the bulk superconductivity ends. So we were wondering whether this can teach us anything about the interplay between those surface states and the bulk. So the next experiment that we did was repeat this, but use larger training fields to train the sample. So again, we cool down with the field turned on through this surface transition, through the bulk transition, and then we turn the field off and we warm up and measure. And now there is nothing at all. Which is very strange. If we had a magnetic order, you would expect that it doesn't care what the field is. If the field is strong enough to align the domains, it doesn't care if you increase the field. Okay. It took us a while, but we have a picture that we think explains all of this. And this has to do, again, with the fact that we don't just measure the surface independently, but we have this bulk superconductor, which maybe preserves time reversal symmetry, maybe doesn't. But the point is that once you pull it down through the bulk transition with the magnetic field turned on, you have vortices. And this idea, well, you have the vortices. Now the question is what these vortices do to your very delicate magnetic state at the surface. And so as you warm them up, warm the sample up or remove the field, those vortices go away. And when they do that, the local magnetic field in the sample is changing. And therefore, maybe you flip those domains. If the coercive field is low, you can flip them. And then as you warm up, more of these vortices move away, and you scramble up your domains, and you erase whatever you have trained. So this idea is not just a schematic. People see similar things in experiments. So this is uranium, cobalt, germanium, which is a ferromagnetic superconductor. So the Curie temperature is 2.5 Kelvin. The transition temperature is 600 millikelvin. What you see here is a squid image taken by Hasselbach group of this material, and all of these things are magnetic domains. And once the sample is cooled down further into the superconducting state, there's some changes in this domain structure. So here's one that I highlighted. So you can see here it goes from black to white. And this has to do with vortices that are coming in and moving around the sample and changing the magnetic field distribution. So it is conceivable that maybe something similar is happening in our case. And this is not just something that other people saw and something I can draw a cartoon of, but it is something that we can test. And the way to test this is just to try a different, why is it going? Okay, just to try a different cooling procedure. So before, I had the field turned on as I was cooling down the sample. through the bulk transition. So the next experiment I'll do is I will just turn the field off before the bulk becomes superconducting. So now I can train the magnetic state that I have had before, but I will not introduce vortices in the bulk that will scramble my memory and ruin my signal. Okay. Here's the data after we've done this procedure. So we completely recover the behavior that we've had before, or this non-monotonic behavior that we still don't understand below the bulk critical temperature, but then there is an onset of the signal at 3 Kelvin. So this is, once you get rid of those vortices, you no longer move around your domains, and you can get your order parameter to saturate, and you can see it when you warm up. Okay, so I think I was too quick. This is my last slide, but this is good because we're kind of running late. So just to leave you with our conclusion, we have done 3 different experiments. We have STM data, we have mutual inductance data, we have polar Kerr effect data. The temperatures, right? This is done of different samples, different growth budgets, different measurement setups. All of them show that there's something going on at around 3 Kelvin. If you look at the mutual inductance and the STM, it looks like superconductivity. If you look at the polar Kerr effect, this is time reversal symmetry breaking. If you combine these 2 things together, we believe that the surface of this material is chiral superconducting. And just as I conclude, I would say there are really exciting new things going on. So Molenkamp group, Claudia Klosser, they can now grow epitaxial thin films of this material. So we could potentially soon make devices out of this and really investigate this in a very controlled way, the surface states and the relationship to the bulk. Okay, thank you very much.